Welcome to the lecture in Philosophy of Science. Last time I ended the lecture with my discussion of the classification of sentences according to the content type, and today I will speak about the classification of scientific statements, sentences, according to their generality, and related to that the logical strength, because the generality of a sentence is important for the diagnosis of the scientific character of a sentence, in particular concerning two questions. As we shall see, the question of law-likeness is one thing, and particularly also the question, the logical nature of the sentence, how it behaves under test operations, to which degree and in which sense it is testable, verifiable, falsifiable, confirmable, disconfirmable. Okay. So we can order sentences according to their generality, prima facie, into these types here. So you see here the most general classification at the left side here. We have general sentences, singular sentences, and existential sentences. And maybe if you just look at those here, the so-called strict generalizations as a first example. So strict generalizations say something about all objects, right? So they are, in this sense, logically strongest. All raven are black, right? This is a very strong statement. Maybe someone asks me, where can you find a gas station? Everywhere, right? Well, that's a very strong statement, nice statement. And then we have singular statements here. These singular statements say something, assert something about particular individuals. This thing says a raven and it is black. That thing, or someone asking me where's the gas station, I'm telling him, well, it's there in this street, so and so, I don't know, corner street 17 at the right side, right? This is a singular statement. It's not so strong, of course, much weaker than a universal statement, but it has still some sharp information. And then there are existential sentences, like there exists something which has these and these properties, like someone saying me, well, there exists a black swan somewhere, I don't know where. That's the weakest form of statement. It's like something, I ask someone, where's the gas station? He tells me, well, somewhere in the city. You know, that's almost no information. Well, of course, there's some gas station, but I don't know where it is, where to find it. So these are existential statements, okay. So most important for scientific hypotheses, of course, are the general sentences. So far I mentioned only these strict generalizations, but actually there are two types of generalizations in science which are significantly different. First, there are the strict generalizations. They may also be called deterministic generalizations because, so to speak, they assert a strictly universal, they make a strictly universal claim, and mostly the universal claim has the form of an implication. For all x, if x is an A, then x is a C. Here A stands for the antecedent predicate and C for the consequent predicate here, right? That is a notion which we will use in further units of this lecture too. So, I mean, you know, there are almost no universal facts which hold categorially. Maybe all living beings must die. But there are almost no facts which all things have in common categorically. But there are a lot of implicated facts, conditional facts, which all bodies have, like things. So, every physical particle has a mass, right? And therefore also a certain energy. And that's a universal statement of this form. All raven are black, right? All A's are C's. So these are purely universal sentences, and but there is also another important type of these statements. They are mixed quantified generalizations, like universal existential generalizations. Like, for instance, I mentioned this example in some of the previous lectures. All substances have a melting point, right? For all x, there exists a y such that Rxy, that's a relation between x and y. All substances, if for every x is a substance, then there exists a temperature such that x melts at this temperature. And you will see soon that universal existential generalizations are still strict because they have one universal quantifier, which is essential. But they have different testability properties than purely universal statements which don't have such an existential quantifier in them. You will see. Good. Now, then we must distinguish here between two types of these universal quantifications, the strict generalizations. The first type are spatiotemporally unrestricted generalizations, like saying all bodies in the universe, all physical bodies in the universe, they are only, for naturalists, they are only physical bodies, physical entities, right? All entities in the universe have mass, right? All two bodies attract each other. These are laws of physics. So you see that spatiotemporally unrestricted and strictly universal generalizations are typically candidates for laws of nature. I come to that later on. And then, of course, which is important for the special sciences, for sciences, say, biology upwards, history and so on, or psychology, we have spatiotemporally restricted generalizations, like all life on Earth is based on reproduction by DNA, right? Desoxyribonucleic acid, DNA, which is a fact of evolution of our human life, but maybe there's life on other planets, in other different galaxies, other solar systems where reproduction is not precisely based on DNA. Who knows? So that is a spatiotemporally restricted generalization. And I come to that later, you know. That's not so sure to which extent these restricted generalizations are law-like. We will see. Good. But all these generalizations are strict in the sense that they have no exceptions, right? You really can deduce from these generalizations something to individual cases, right? And if all humans must die, then you must die too if you are human, right? If the antecedent condition is satisfied, right? That is clear. And if, well, all people in that room are younger than 60, then I'm younger than 62. I'm probably the oldest here. So that is a deduction. This is different for non-strict generalizations. The most important kind being statistical generalizations. They have the form here, we call A is antecedent predicate, C the consequent predicate. They have the form so and so many % of the A's are C's, right? Or the probability of C given A is R, where Q is 100 times A times R, right? 80% of all A's are C's, or the probability of C given A is 0.8. Small little b is here the statistical probability. And this is a statistical generalization, and you can depict that by in the form of a Venn diagram, right? If this is a picture of the set of A's, right, then 80% of the A's or C's can be drawn in that way. So these are the C's, right, and these are the C's and A's. And if the probability of C given A is 80%, then this means that this is 80% of that area here, right? So for instance, there right, 8 guys are in here and 10 guys are in the full A circle. Well, these are statistical generalizations. Again, we have the distinction between spatio-temporally unrestricted generalizations and spatially temporally restricted generalizations, right? I mean, in the finite case, right? Yeah. If you have a really unrestricted generalization, like saying like 80% of all humans are dark-eyed, whatever at any time point in the history of humanity. This is an open-ended time scale now. This would be an infinite statistical generalization. Then we may discuss whether these are also candidates of laws of nature. We will discuss it soon. But what is important is that these non-strict generalizations admit exceptions, so you cannot deduce anything, right, from them to the individual case. This is important, right? You cannot deduce anything from an assertion that 80% of all Italian people are brown-eyed, say, to this particular Italian guy, right? Because you don't know whether it belongs to the 80% which are brown-eyed or to the 20% which are non-brown-eyed Italians. So this is, you say also, you express this also by saying non-strict generalizations admit exceptions, and you don't know where these exceptions are. So you can only infer with probability to the individual case, but not with, you cannot anything deduce. That's important. And in this sense, strict and non-strict generalizations behaves very differently, which is by a layman and by lots of not so informed people often underestimated or overlooked, right? Because, you know, if you know something about, if you have a universal generalization, right, for every person, if the person doesn't eat, say a certain mineral, then this person will get ill. Then, of course, it's easy for the doctor to say, well, you have to eat this mineral, otherwise you will get ill, right? You have to take your magnesia or your calcium, otherwise your muscle won't. In the case of magnesia, your muscle won't work anymore. That's for sure. So in that case, if you have a universal generalization, you can deduce it you can derive that to the single case. Nothing can happen. But if you have a statistical generalization, for 80% of all people, this and this therapy is the right therapy for this and this sickness or illness, right? Then you cannot automatically transfer that to the individual patient, because maybe the patient belongs to the 20%, and the doctor must not simply transfer the statistical law to the individual case without a sharp diagnosis of the individual case, which collects all maximally specific knowledge about that individual case, and then the doctor can evaluate and decide which therapy is best. For instance, of course, if you have influenza, and penicillin vaccination is good, but you know that there are 5% or something people which are allergic against penicillin vaccinations, and for them a penicillin vaccination may be deadly even. So, and if the doctor doesn't check that, right, then the doctor's, in that case, the physician is irresponsible, so he didn't understand the nature of a statistical law. You cannot deduce it that it will be good. If it's good for 95%, that doesn't guarantee you it's good for this person. So, in the literature, this problem of applying statistical laws to the single case has been called, and the principle what you apply here has been also called the principle of the narrowest reference class. And it goes back to Hans Reichenbach, which I have already mentioned several times. And it says that if you have a statistical a set of statistical information, statistics laws, statistical generalizations, and an individual then you must conditionalize your statistics on the most specific information of that individual which you have, right? So that's the important thing. For instance, for 95% of individuals, penicillin vaccination is good, but if you know this individual is allergic to penicillin, you don't infer that's good for this individual. You infer rather from the more specific information that you shouldn't vaccinate this person with penicillin, which is obvious and clear. Good. This brings me to a related point here, namely that if you speak about probabilities, there are two kinds of probabilities in science. There's the statistical or objective probabilities. They always refer to classes and never to individuals, like saying like 80% of all Italians are brown-eyed. This is a statistical probability, right? And if I say something about a particular person, then I can only say this. If I apply a probability to a particular individual, then I have no statistics. It's just one individual. There are no relations between frequencies in classes here, right? No repeatable kinds of individuals. Then what I apply is so-called epistemic probability or subjective probability, which is an expression of my degree of belief, right? My rational degree of belief. So I can say with high probability, Vincenzo, the Italian guy, is brown-eyed, or with a probability of 80% in that, Vincenzo is brown-eyed. But again, this is only reasonable if all that I know from Vincenzo is that he is an Italian guy. If I know from him he has blue-eyed parents, then I know with certainty that Vincenzo will be blue-eyed too, and that follows from Mendel's law, right? So with this more specific information, it makes no sense to transfer the statistical law to the individual. It must, in its reference class, contain all information which I have. Then I can transfer it. So this is a side remark on how these generalizations work. So, and now let me finish this kind of classification. We have again spatiotemporally unrestricted versus restricted statistical generalizations, of course. And then there are some kind of non-strict generalizations which are like statistical generalizations, but they don't tell precise percentages, precise numbers, right? But they are just, for instance, what you call anormic generalization, says most of the A's are B's, or A's are normally C's in that case. A's are normally C's. Most of the A's are C's. High percentage, something which is normally the case, but you don't specify a number here. Or another kind of non-strict generalization is ceteris paribus A's are C's. This means something it's similar than the normic claim, but it says if interfering factors, disturbing factors, are absent, then A's are C's. So A's, which are normal instances in the sense that there are no interfering or disturbing factors around, which produce exceptions, are C's. Right? Good. And then just to go down the full classification here, you have, as I said, these singular sentences, then you have these extensional sentences, and you have, of course, mixed sentences. I mean, you can have a conjunction between a universal statement and an existential statement. That would be a mixed statement, but that is not really important. Just a mixed, trivial mixed case. Any questions so far? Yes?
R should be smaller than 1 and larger than 0, right? Because it's a non-strict generalization.
Yes. Well, the extreme case of a statistical generalization is 100%. Sure, and the extreme case in the other direction is 0%, though I include this case. But you're asking a question. So the sentence, all f's are g's, for all x, if x is an f, then x is a g, implies by logic that the probability of g given f is 1. Right? You are thinking that the other direction should also hold. That is not necessarily the case. It is only the case if there are only finitely many f's. If f is finite, if the antecedent class is finite, then a probability 1 implies also the strict generalization. But if it's infinite, it's not the case. You might have even infinitely many exceptions. If the reference class is infinite, statistical probability is defined as a limit of a frequency in a random sequence. And for instance, and if these the finite frequencies converge to 0, then the probability is 0. For instance, the probability of finding prime numbers among natural numbers going one by one, the limiting frequency of them is 0, right? But they are of course prime numbers. Or the limiting frequency of numbers which are integers of 2 to the power of n, integers of integer powers of 2, right? 2 to 3, 2 to 4, integer powers of 2 goes to 0, because n divided through 2 to the power of n, for n to infinity it goes to 0. But there are of course natural numbers which are powers of 3. So this, in the interesting case where this is not finite, where the statistics is over a potentially infinite class, one probabilities are weaker than universal generalizations. That may be important information. Any further questions?
On the next page.
Yeah.
So the subjective.
Yes.
Subjective probabilities. So you say it refers to individual cases. You mean also refers to individual cases, right?
Yes. I mean, it didn't speak about other things. It always refers to statements, to propositions, right? And not to open formulas, to classes. It could also be hypotheses, but particular hypotheses, of course. But I didn't speak about that, yeah. So, I continue with listening. The most important logical relations between the statements which I've just presented in my classification. This is just for beginners, that part of logic which you really must know to understand basic philosophy of science, right? So this double arrow stands for y, follows logically from x, and there are these relations. First, a universal sentence implies a corresponding singular sentence. All A's or C's implies if this individual, small a, right, denotes an individual, if has the property capital A, then it has the property capital C. So that is, of course, clear. It shows that universal sentence implies singular ones. So they are stronger. The next important kind of logical inference is a universal sentence and a singular sentence which instantiates the antecedent predicate of the universal sentence implies a consequent universal sentence. Like all A's are C's and this individual is an A, therefore this individual is a C. If all humans are mortal and I am a human, then I am mortal. This is also called, has also been called, the deductive nomological explanation schema, and it is very important in the history, in the discussions of scientific explanation, this kind of inference. Deductive nomological, because nomos means a law, so all A's or C's is taken as a law, right, a law of nature, for instance, and deductive because it's a deduction, it's a deductively valid inference. Third, falsification. A suitable singular sentence falsified is strictly universal sentence. Falsification scheme 1. So singular sentence implies a negation of a universal sentence. For example, A is an A, this individual is an A and not a C, therefore not all A's are C's. This is an inference here. For instance, this individual is a raven, but it's not black, therefore the hypothesis, the generalization, all ravens are black, is false. This is called a falsification. The second kind of falsification scheme is similar, but you have an existential sentence. Also an existential sentence can falsify a strictly universal sentence, so it can imply the negation of a universal sentence, somewhere tells you there exists an individual which is an A but which is not a C, therefore all A's or C's is false, right? For instance, so an existential sentence falsifies a universal sentence. For instance, in that case, I believe that all swans are white, and someone comes to me, no, in Australia there exist swans which are black, right? I believe these people. I haven't never seen a black swan. I don't have a singular sentence which falsifies the hypothesis, but I believe in the existential sentence. So again, I know the sentence all swans are white will be false. Even here a stronger claim can be made, and that is something which was important for Popper and can also be called the Popper scheme 5, namely a universal sentence is actually equivalent to the negation of an existential sentence. So if I say all A's are C's, this is equivalent, so the logical implication goes in both directions now. This is equivalent with saying there is no A that is not the C. So the extent sentence, the existent A which is not the C is false, right? On this reason, Popper always emphasized that laws of nature are prohibitions, right? They prohibit certain states of nature. That is the philosophical outcome of this logical fact that a universal statement is equivalent with saying certain possibilities are never the case. So certain existential possibilities do not occur in nature. Okay? So that is this Popper scheme 5. And then 6, we have the following logical relation. A singular sentence logically entails, of course, an existential sentence, which again shows an existential sentence is again weaker than a singular statement. So if I know this individual has a property A, or is an A, then I know that there exists an individual which is an A, right? That is clear. Finally, what is the relation between statistical or non-strict generalizations and singular statements? I already said that. Already revealed this surprising fact. There are no logical consequent relations between non-strict generalizations and singular sentences, right? There are no. There are only relations of statistical and epistemic probability, prima facie relations of epistemic probability, but if you consider classes of singular statements, you can also have something like statistical probability about the truth values of singular statements, which is needed in some statistical techniques, like for calibration theorems and things like that. Okay, so far. Now, we come now to the first question, which is related to these logical differentiations between sentences according to their generality, namely, what are laws of nature, right? What is it to be law-like? And the idea of all empiricists, even of the logical empiricists, right? Carnap, Hempel, and until I would say until the 50s even, 1950s and 60s was, spatiotemporally unrestricted strict generalization, that are the prima facie candidates for proper laws of nature. So you say, although they are law-like, that means so much that if they were true, they are laws of nature. For instance, here examples like all physical entities attract each other. So for all x and y, if x and y are physical particles, then x attracts y and y attracts x. So that is a full logical formalization of this law. The law of cavitation in classical physics is an unrestricted law. Perfect. Or take a law from chemistry, the ideal gas law, which roughly says for ideal gases X, the product of the pressure times their volume is proportional to their absolute temperature. Or more precisely, the product of this pressure and volume is constant, the gas constant, times the mole number, so the number of the molecules, times the absolute temperature of the gas. So it's another example for a strictly universal spatiotemporally unrestricted law. Now, can we say that these are the law-like sentences? This is called the problem of law-likeness, and the problem is not every sentence that is a spatiotemporally unrestricted and strict generalization, even if it is strict and even if it is spatiotemporally unrestricted, right? According to its logical type. So even not every sentence which has these logical characteristics is a law-like generalization. That is a problem, and here's an example. Again, these examples goes back to Hans Reichenbach, so you see I mention this philosopher very often. Compare this to strict spatiotemporally universal generalizations. No lump of radioactive uranium has a diameter of more than 1 mile. In the universe, right? Versus no lump of gold has a diameter of more than 1 mile. Assume that both are true. I mean, what would you say? What is the difference, or what do you think? Yeah?
Well, first of all, they're not particularly precise, and secondly, it's not...
Why?
According to...
Why are they not precise? I think they are perfectly precise.
Well, it could be a more precise statement if it was to say more precisely how large the diameter of radioactivity.
Yeah, the maximal diameter.
I think the more important point is...
No lump of this kind of substance, it's precise, has a diameter, takes the maximal diameter.
Yeah.
Of more than 1 mile, that is also precise.
Well, I think the more important point is that we wouldn't really be surprised if we now found one that has a larger. We might be surprised, but it wouldn't be so surprising because it's not forbidden by any fundamental laws.
No, it is. There is a difference. Does any other one know?
I know, of course.
Yes, say.
Well, because in the first case, there's a critical mass that's reached that doesn't allow such a lamp to exist, right?
Exactly. So that's the point here. Radioactive uranium, one with a diameter of 1 mile, would exceed the critical mass and it would immediately explode. I mean, it already exploded at a much smaller lump stage, right? It cannot be by law of nature. Such a lump of radioactive uranium with a diameter of more than 1 mile cannot exist. It's forbidden by law of nature. That is a law of nature. The first statement is a law of nature, the first generalization. But the second, probably it's true. There's probably no ball or lump or whatever of gold with such a diameter in the universe. I mean, how? It's so... But it's not excluded by law of nature. I mean, there could be a foreign intelligent species in a different galaxy which just collects all the gold. I mean, it's absolutely improbable that by ordinary solar mechanism where the matter is produced, like something is created of that sort, which is pure gold and not other metallic elements in it too. That's so improbable. But I mean, there could be very specific reasons. There is no law of nature which excludes that, right? But there's a law of nature which excludes that. But the difficulty is, no, look, the logical empiricists thought that by logical characterizations of this sort, spatiotemporally unrestricted, strictly universal, we can distinguish, we can characterize law-like statements. But you see here now, unfortunately, that doesn't work. Because all logical characteristics and spatiotemporal characteristics of the two are the same, right? They have exactly the same form, or the spatiotemporal breadth, right? Application range is the same. But still, we would say one is a law of nature and the other is not. And this is a law of problem of law-likeness, and this had a significant influence on the philosophy of science development since the 1960s, because then one saw that these old metaphysical questions, what is physical necessity? I'm not speaking about logical necessity, but not speaking about contingent truths. What is physical necessity? Came up again in philosophy of science, and we saw that we need these notions. Obviously physicists have this notion, and we don't know exactly what it is. For instance, famous suggestions, for instance, also by David Lewis or by Van Fraasen, here in this respect they had very similar suggestions. They say, well, physical necessity is that what follows from our best theories, right? And the best theories for David Lewis were those theories which are most unifying. So, you know, in that case, this cannot be, that this is false, follows from the accepted physical theories which are best unifying our huge body of empirical regularities, of empirical knowledge, right? Of generalized empirical knowledge. While this hypothesis, no physical theories forbids it. So, this is a problem of law-likeness. It's an interesting problem. And still today, there's a controversy about what is the nature of law-likeness. Good. So, thank you. So, let's go on now to the question of law-likeness for the spatio-temporally restricted generalizations. And here it's even more difficult. It turns out, in the end, that law-likeness is graded. Somehow graded. That's at least the opinion of those philosophers of science to which I belong. I would say it's graded. But look, for instance, look at these examples. 5 examples here. The first, all bodies close to the surface of the Earth fall downwards with a constant acceleration of 10 meters by the second to the square. This is Galileo's law of gravity. It is spatially restricted because it refers to the surface of the Earth, particular spatio-temporal region, right, with a certain boundary condition, namely the strength of the gravitational field and also its homogeneity, its direction. But it clearly is a fact, a law-like fact, that in that gravitational field the acceleration is such and such. No doubt about this. It's a paradigm case of a derived law of nature, as one also says. Here, let's go to biology. All mammals in polar regions have a more rounded form than their conspecifics in warm countries. This is called Bergmann's law in biology, and it's an interesting law. Does any one of you have an idea why this holds? I mean, yeah? Yeah, exactly. It's because the volume increases with a third potence of the distance, and the surface is a second. So the relation of surface to volume, or of volume to surface, let's say, gets bigger if the body gets bigger, and also it gets bigger, this relation, if the body gets more round, because rounder form need less surface. See, this for same volume, the round form needs least surface. Therefore, of course, in cold regions, it's good to have a small surface because you don't want to lose temperature and heat, right? So therefore, the organisms of the same species there tend, or the same genera there, tend to have rounder and larger forms, while in the hotter areas, like in the desert fox, like, is small and very thin and flat, because it's good, if you want to lose heat, it's good to have a big surface compared to your volume, right? So this is there's an explanation. There is some law-likeness here, right? But this law is not as strict as that law. It's not guaranteed that evolution will bring that out, right? It's not guaranteed that evolution always works. Well, I don't know. Maybe in the polar region there are predators. They eat up all. They like very strange predators, right? They just like the round, large forms, right? They get eaten, right? And then that's peculiar situations. Then of course the polar the polar organisms in polar regions at the North Pole want then to get these round and large forms. So there may be exceptional situations where the evolution doesn't lead to that situation, but as a certain evolutionary trend, it's certainly law. It's less law-likeness than 1, less law-like than 1, but 2 is still law-like. What about 3? Until approximately 10,000 years before Christ, all humans lived from hunting and gathering. That's a law, I would say a generalization. Let's speak about generalization, the typical generalization of global history. Do you think it's law-like? Or at least it has something in it which is law-like, which is somehow not an accident, not just a contingent accident? Of course not the time point. I mean, you know from the previous sections, time is an interval scale, so the 0 point of the time, that is arbitrary. But that there exists some time up to before that time, all humans lived from hunting and gathering. And afterwards, this was no longer so, even though this was significantly different. If there's something in it, do you have an idea? You?
Seems less law-like than the others.
Well, I would say the following. Obviously, it's an invention of agriculture. And agriculture, it's a quite advanced technology for which we really need a lot of skills, intelligence and social skills too. So while feeding from hunting and gathering is a primitive form which humans share with animals. So from that view, when it is clear that before agriculture, the first and most primitive form of feeding is hunting and gathering, and so it's the first. Yeah. And then that's the first thing which is involved in this first non-accidental thing, right? Hunting and gathering is a primitive form of feeding, and then agriculture, that's the second thing, if it develops, has really significant evolutionary advantage, so it spreads. And so it replaces hunting and gathering, then not necessarily instantly, right? But it tends to spread. So this is still something which is law-like in that law, in that generalization. But it's still less. Then look, in the Middle Ages, all agriculture was based on the feudal fief principle. I mean, that I would say that is a historical fact. I mean, I don't see much law-likeness behind that, right? And the extreme case would be generalization like that. All apples in this basket are red. I mean, that's obviously what you call an accidental generalization. It's from its logical form, it's a spatially restricted, right, strict generalization. But as I said, you know, by background knowledge, there can only be a few number of apples in this basket, so it behaves actually like an observation sentence. Now I come to statistical. Yes? Okay. If you have a question, please.
First of all, you said that 4 is a fact and not so law-like. Mm-hmm. But couldn't you still apply this deductive nomological model and say, well, maybe not for an explanation, but you could perform a critical test and say, okay, we're going to look at one particular region in the Middle Ages and see whether the feudal fief principle applies, and then if it applies, we say, okay, so it passed the test, or if it doesn't apply, we could say the general hypothesis is false. You could still do that, right?
Yes, but maybe I repeat that. We are not speaking about testing the truth value of a strict generalization. We are saying a strict generalization. There are two questions. Is it true? Yeah? And if it's law-like. And these are distinct questions. Even if it is true, it need not be law-like. So if you test for truth, it doesn't tell you whether it's law-like. But you can also ask the question of law-likeness independent from the question of truth. Would it be a law if it were true? So these are simply different questions. That's the point here. And which positivists and empiricists really overlooked. I mean, they really thought that this would be somehow one thing, but that is not the case. Yeah?
My point is just that for the way we epistemically deal with the sentence, it doesn't matter so much.
You're right. For finding out the truth value, it doesn't matter so much. I give you an interesting example. We know that our universe consists totally of matter and not of antimatter. At least our universe. Say so. Is this a law of nature or is it a contingent fact? I mean, who knows? Who knows, right? But for the epistemic question of truth, just we can forget that question. That's clear. Okay. Further questions? I mean, no. Then I go on. A similar thing can be said about statistical generalizations, but here we have an additional complication which I want to mention, namely, if we have a statistical generalization, we should ask ourselves first, so if it is spatiotemporally unrestricted, we still have here a new question which doesn't arise for strict generalization, namely, the fact that we have only statistical knowledge here may be either due to our lack of knowledge, in that case it is an epistemic indeterminism, or it may be due to the fact that nature itself is not determined by strict laws. This is called the position of indeterminism, and in that case we speak of an objective indeterminism. And the second question is, if statistical generalizations are spatiotemporally restricted, like here, then again their lawlikeness will turn out to be graded. These are the 2 points to be made for statistical generalizations. And now let me speak about that in more detail. Here we have the first example. 50% of all cesium atoms of the mass number 137, for any amount of substance which you have, will have decayed within 30 years. Cesium atoms, 107, are the major radioactive contamination of nuclear accidents of the super-Gauss, the nuclear accidents of melting of the core of the power plant, which happened in Chernobyl and which happened in Fukushima. Cesium 173. And you still have it following from as a consequence of the Chernobyl accident in 1997, you still have it in our European countries. Although now it's more than 30 years, but still 45% of that is still around, and in particular it is collected by all these mushrooms. So if you go mushroom collecting, they collect cesium-107, you find a very high percentage now. It's still a danger in the woods if you collect mushrooms, right? So I like to collect mushrooms, so I'm acquainted with that. But I have experienced the Chernobyl accident very lively, right, at that time. So it's very close to it, actually, and so that was an experience for me. So that is a quite important statistical law-like statement. Now back to the philosophy of science thing. This is a kind of objective determinism. It's a statistical law of nature. Why? Because, we know that these radioactive atoms, they decay sometime, but it's impossible to predict when a particular radioactive atom, a cesium atom, decays. You cannot predict it, even if you have full physical knowledge about the atom. It's an unstable process. But what you know is that statistically, if you have a large number of atoms, approximately 50% of them have decayed after 30 years. So this is a typical example. And you know, in the time of Newton, in the 80th and the 19th century, in the time of classical physics, physicists thought that the true laws of nature, all of them are strict. So God has made perfect, strict laws that are ruling our universe. This was the idea of the Laplacian demon who can predict everything. The idea was Laplace, which was a very important physicist after Newton, has this idea that if you have a complete knowledge of the state of the universe at one time point, then if you know all the laws of nature, you can perfectly predict the whole future of the universe. And whether you can also predict the whole past of the universe. In modern physics, following from quantum mechanics, quantum physics, this viewpoint physicists were forced to give up this viewpoint, right? So now we accept genuine indeterministic laws, and this is an example of a genuine indeterministic law. Okay. Now take the next examples. 80% of all lung cancer patients or lung cancer sufferers were heavy smokers. I mean, this is a statistical generalization, right? Which is certainly law-like. It's law-like that smoking increases the tendency of lung cancer strongly, and that it is a major cause for lung cancer. But it's not an objective indeterministic law, because if for a particular person, if you know the physiological state of a particular person, we can predict which much higher or much lower, which much sharper, can make a much more certain prediction about whether this patient will develop lung cancer or not, right? For instance, a person who had worked in the coal mine without being a smoker might develop lung cancer too. Or a person who has smoked but very light cigarettes and then somehow, based on his physical constitution, does not develop lung cancer. There's no signs of them. May also be possible. If you have a very precise knowledge of this particular person, then of course this probability value changes. So this law is this indeterminism here is an epistemic indeterminism, right? Although it is obviously also a law-like statistical generalization, but the indeterminism involved here is of the epistemic nature. This should be clear. Now let's go to some more special sciences, like psychology. 70% of all bedwetting children have parents with a disturbed relationship. What do you think? Is that law-like? And if yes, what is the difference between 2 and 3? What would you say? Any ideas? You maybe?
Well, I mean, again, it might be underlying causes that make it as law-like as number 2, number 3.
But I think there's a difference between the two. And I mean, there's a theory about that difference in terms of robustness. You say that a statistical generalization is robust, right? It's robust. This, for instance, philosophers of science like Woodward or Strevens or others have used this notion. And statistical generalization is robust if it holds under a lot of varying circumstances. And I mean, this generalization really holds under a lot of varying circumstances. I mean, the probabilities may change, of course, under the circumstances a little bit, but the correlation does not change. While the bedwetting children have parents with a disturbed relationship is more or less based on a certain social family structure. In German, Kleinfamilien, the more bourgeois type or Western type of classical families, which you call in Germany Kleinfamilien, so the mother, father and children, that is a family. I wouldn't know an English term for the German word Kleinfamilie, but traditional families. While in earlier culture, I mean in larger family, structure where you have family clans, where all the grandparents are, and the uncles and aunts are included in the family, you don't have this so much, because if the parents have a disturbed relationship, and as a consequence of that, they don't take so much care of their kids, so the kid is not protected and beloved as it should be, then the grandma, the grandpa, or whoever in the large family clan takes over this role, and therefore in these social structures it will be not the case. Therefore this statistical generalization 3, it's much less robust than 2, and in this sense it is less law-like. And now, of course, you have examples of that thought. 70% of all Swedish people are Protestants. I mean, that is more or less a historical fact and not really anything law-like here. And 60% of all apples in this basket are red. I mean, that's an accidental statistical generalization, that's for sure. Yeah. Also, two final remarks on generalizations of the statistical kind. You have also weaker kind of generalizations, which I just am listing here. For instance, you may have qualitative statistical generalizations, where you just say most bedwetting children have parents with a disturbed relationship. This corresponds to what I called, this is related to normic laws. You may also say, normally birds can fly, most birds can fly, most bedwetting children have parents with disturbed relationship. In that case, normally is maybe not the right phrase, but the common feature from a statistical viewpoint is that they are numerically unspecific, these most generalizations, they're qualitative. And then you have an even weaker kind of statistical assertion or generalization, namely the following. Bedwetting children are more likely to have parents with disturbed relationships. Here you just say that a certain factor A increases the probability of a certain factor P or C. This you call also a positive correlation. So if you hear that statement, there's statisticians, whatever, scientists, psychologists have found a positive correlation between A's and C's, like between eating sausage and cancer rate, right? Then this is a very weak assertion, because it doesn't tell you how strong the effect is. To which degree A increases the probability of A. It just says, we are quite sure strong correlation means you can be very safe that there is a certain probability increase here, right? That is a correlation, probability increase, or a negative correlation would be a probability decrease. I will turn to that topic later on in the talk. So this ends my section on the classification of sentences according to their generality and the question of law-likeness. Are there any questions so far? Yeah.
You mentioned already that there is a big difference between epistemic status of strict generalizations and statistical generalizations. Maybe that, we tested totally different regarding the truth. But what about the law-likeness? The theories on law-likeness, is there also a big difference between between strict generalizations and only statistical ones, or do they try to grasp both in one at once?
I think several aspects of statistical generalizations and of the law-likeness of statistical generalizations and strict generalizations are common to both. Yeah. So several criteria are the same. One thing is clear. If you have spatio-temporally restricted generalizations, then we have a similar effect of the gradedness of law-likeness. That is similar. I tried to show that with my example. Second, I'll give you now a list. That's the first thing. Second, what is important? Second, if there is a spatio-temporally unrestricted generalization, then in the statistical case it is important to know whether it is objective or epistemic. If it is epistemic, it is not fully law-like, right, so to speak. There is always something contingent involved. So in this sense, epistemically, statistical generalizations which are statistical on epistemic reasoning, on epistemic reason, like the lung cancer example, are never fully law-like, right? There is always some contingency involved. In that case, they behave like spatially restricted strict generalizations. But you know that I told you that there are also unrestricted strict generalizations which are still contingent, or which involve some contingency. So this is difference number one. And difference number two is also interesting, namely this question of the robustness makes good sense for statistical generalizations where you can restrict. Here you just have a statistical generalization which goes over a total domain, right? And then you consider certain subdomains characterized by qualitative properties, and if the probability varies strongly, then it's not very robust. You cannot do a similar thing for strict generalizations because of the monotonicity. If it's strict, holds for the total domain, it holds also for all subdomains. So the question of robustness for strict generalizations is not really discussed in the literature. It would be something like, it doesn't really apply.
And for example, Goodman says, for example, that we should try the counterfactual test. Yes,
I didn't speak about that. You're fully right. But my view on that is that my view on that is the following. Take the following example. So I say the counterfactual test is not a test because we can decide about the truth value of a counterfactually only to the extent in which we already have a belief whether the generalization, the non-counterfactual generalization, is law-like or not. That would be my position, and I give you the following example. So I mean, of course, if I would let that go, it would fall down. I mean, that is sure, because it's a strict generalization. And all apples in this basket are red. If I would put that green apple into the basket, it would turn red. That's nonsense, because we are sure that's not law-like. But now look at the following example. If I, or if you, would live 10,000 before Christ, then would live on hunting and gathering and not on agriculture. Is that true? We don't know whether it's law-like, right? That's a good example. What is a counterfactual situation? Do you, in the counterfactual situation, have your knowledge of what you have now? If I would live 10,000 before Christ, or 12,000 before Christ, I would immediately start agriculture, of course. Or would I then be like these people at that time? So it's just unclear, because that's not clear whether this is really law-like, right? So this shows that Goodman detected absolutely right. So this was a discovery that a sentence is law-like if we are ready to assert the corresponding counterfactual is true, but it's not a really test criterion. That's my opinion. But it's a very good question, thank you. Okay, coming to the last part of this lecture today, I speak now about the difference between the different kinds of sentences according to their generality. What difference does this make for the testing of these sentences? And it makes a significant difference, as you will see. For working that out, you have distinguished these four notions. You say a hypothesis is verifiable if it follows logically from a finite and consistent set P of potential observation sentences. This means the hypothesis is verifiable. So, important here is potential. So, for instance, the hypothesis that there's a black pencil here, this is of course verifiable because it follows from my observation sentence there's a black pencil, right? It follows from a set of observations, right? Or the hypothesis that there exists a pencil. but also the hypothesis that say, behind this door, right? Behind this door, there is a person staying, is a verifiable hypothesis because it follows from a potential observation. I can open it. I don't do it now, but I could. Let's do it. So no. So you see, it's wrong. I have falsified it in that case. There is no person behind the door. So these are verifiable hypotheses, or falsifiable ones. What does it philosophically or epistemically mean that a hypothesis is verifiable? I mean, we are fallibilists, so we don't assume that observations are, so to speak, absolutely certain. So what does it mean? It does mean, if I trust my observations, then I can be sure in the truth of the hypothesis, right? If I make the corresponding test. That means verifiable. So to the extent, so the certainty which I can have in this hypothesis is no less than the certainty which I can have in my observations. That does it mean, verifiable. Okay, but and singular sentences are typically verifiable. Singular observation sentences are typically verifiable, of course. Confirmable means a hypothesis is confirmable. This is weaker. So confirmable, this may be weaker. It means that the hypothesis is just made probable by the assumption of this set B of observation sentences. So, for instance, typically, universal hypothesis, all raven are black, universal hypothesis, and now the point is important, if they range over a potentially infinite domain, so it's impossible for you to observe all the individuals in the domain. If that is the case, it's impossible for you to do that. This is what I mean by potentially infinite. These unrestricted universal hypotheses, they are not verifiable because you can observe only a finite number of ravens. And if all of them which you have observed were black, this means that the hypothesis is confirmed, though it is made probable by this observation. Probable in the sense of an inductive probability measure. Right? That is meant, you must have a certain inductive probability, inductive principles inbuilt in your probability measure, and then it does make it probable. But more cannot be had. You cannot be certain. The future may also show you a new counter instance. So that means confirmable, but not verifiable. Also note that confirmable, of course, every hypothesis which is verifiable is confirmable, right? Namely confirmable with probability 1. So, but not every hypothesis which is confirmable is verifiable. So verifiability is extreme case of confirmability with probability 1. And if I say a hypothesis is merely confirmable, I mean it's confirmable but not verifiable. The same can be made with falsification and disconfirmation. You say a hypothesis is falsifiable if its negation follows logical from a finite consistent set B of potential observation sentences, right? That is falsifiable if the negation of the hypothesis follows. So right, in that case, I have falsified the hypothesis that there is a person in front of the door. Now it's falsified, right? I can do that. The interesting thing is, I can also falsify the hypothesis all raven are black. I mean, I never did it, but it's possible because the observation of one single white raven would be sufficient to falsify the hypothesis. On the other hand, existence sentences are precisely the dual of universal sentences in regard to testability. If you have the sentence, there exists a unicorn. You know a unicorn, a horse with a horn? Old antique mythos of unicorns, a unicorn. Somewhere in the universe, somewhere in the universe, say, this is an existential sentence. Right? And an existential sentence can, of course, dually the universal, purely universal sentences, it can be verified. if there would be a unicorn behind the door and I would open it and you would see the unicorn, then it would be verified, right? There exists a unicorn. But it cannot be falsified because, you know, the universe is potentially infinite and there are only finitely many observations. If I didn't find a unicorn in a finite part of my observation space, that doesn't mean that it doesn't exist somewhere else. So this is, of course, to do with the fact that the negation of an existential sentence is equivalent with a universal sentence, this duality in respect to testability. So a purely existential sentence cannot be falsified, right? But of course it can be disconfirmed. And you say a sentence is disconfirmable if its negation is made probable by the assumption of a set of observation sentences. It's made probable. It's merely disconfirmable if it's disconfirmed but not falsifiable. Again, falsification is disconfirmation with probability 1, so it's extreme case of it. And in that case, I mean, if no unicorn has been found on our planet so far, it's very improbable because unicorn are an imagination consisting of living organisms on our planet. So why should there in another part of the galaxy be a being which looks like a horse but has a horn if it's not on our planet, right? So it's extremely improbable. So of course there exists no unicorn can be disconfirmed. It's very improbable that this is true, that there exists a unicorn. That this is true, that is very improbable. But it's not falsifiable. Good. And now we can have a classification. We look, these four notions we can sort out which testability properties different kind of hypotheses have. And this is a final table. So first of all we have empirical hypotheses. Now first of all take the spatio-temporal restricted empirical hypothesis. Empirical hypothesis and empirical law hypothesis or empirical generalizations, right, of any sort. Empirical means, as you know already, all of the non-logical concepts are empirical concepts, so they are empirically measurable, observable, or measurable by certain measurement operations, etc. If the hypothesis is spatio-temporally restricted in a way such that the region is small enough that we can observe every individual contained in that region, right? Then of course empirical generalization is verifiable and falsifiable because it can just check every single individual, so it behaves like a long conjunction then. If on the other hand an empirical law hypothesis is spatio-temporally unrestricted, then things are different. If I have a strictly universal hypothesis like all ravens are black, this one, I have it already here, then, as I already have pointed out, it is not verifiable, but it is falsifiable. And of course, it is confirmable, as I explained, in the weaker sense of being made probable, inductively probable, by a large set of confirming instances. But things are already different for universal existential statements, right? Like, you know, purely existential statements are not falsifiable, but verifiable. As a result of that, a hypothesis of the form all substances have a melting point or maybe or a boiling point or whatever is neither verifiable nor falsifiable. Yeah, it inherits the non-falsifiability by its universal quantifier, right, from universal statements. It have some, here the existential quantifier, inherits its non-falsifiability by its existential quantifier from existential sentences, right? So I mean, it's not falsifiable because if you found one substance which so far has no melting point, you have observed only a finite number of temperatures. We could melt at a much higher temperature, right? And it's not it's not verifiable, because even if for all substances which you know you have found a melting point, there could be found a new kind of substance in the future which has no melting point. So, universal existential statements are neither verifiable nor falsifiable, but of course, since we assume they are empirical, they are confirmable and they are disconfirmable. They can be made probable or improbable by sets of observation statements, right? The statement all substances have a melting point is very probable, because so far for all substances we found something like that. I mean, it's really chemically, it's not strictly true, there are exceptions here, but I don't go into the chemistry now. It's just the logical fact which is important here. Okay. So what is about statistical empirical generalizations? Well, the same thing as I already told you. If these statistical generalizations are unrestricted, which we assume here, they are not verifiable and they are not falsifiable, simply because there are no logical relations between statistical generalization and single observation statements. But there are statistical test procedures by which we can make it very improbable in the epistemic sense that a statistical hypothesis is true. We deal with this statistical operation in the next unit, in the unit after the next unit. So for instance, if I say, well, 80% of all Italian people are brown-eyed, and I draw a random sample of Italian people, and I find that only 50% of them are brown-eyed, then the hypothesis, depending on the size of the sample, is made improbable by that. It's disconfirmed, as we say. And if the sample frequency coincides with the predicted frequency of the hypothesis, it's confirmed. So they are confirmable and disconfirmable. So what we learn here is that this asymmetry here, that laws of nature are not verifiable but falsifiable, this asymmetry was one of the major claims of Popper in his logic of discovery. This asymmetry of verification and falsification for laws of nature. He made out a whole book of this thing. But you see, it's really restricted to a particular case of hypothesis, namely strict, spatio-temporally unrestricted, purely universal generalizations. It doesn't hold for mixed quantifier, it doesn't hold for statistical hypothesis. So this Popper asymmetry is located here. Finally, theories. Theories are systems of statements, of scientific principles, where these now contain theoretical terms, theoretical concepts, and theories are systems in the sense of having some parts which really are said to be the core of a theory, and some other parts which are more or less peripheral, called the periphery of the theory. And I will speak about theories in the last part of this course. So in some sense I anticipate here now something which I discuss in detail later. But it turns out that if the theories have empirical content, theories with empirical content, they are still neither falsifiable nor verifiable. Even if they are formed with strict statements, this has to do with another problem, the called Duhame's problem of falsification of theories, and I will explain that to you later. But here we have a similar picture. They are not verifiable, not falsifiable, but of course, if the theories have empirical content, so if they have observation consequences, if they imply something for our observations, then they are at least confirmable and disconfirmable. While if you have theories without empirical content, of course, which have no empirical consequences, then these are even not confirmable and disconfirmable. And this concludes this section of my today lecture. Yes, please, questions. Yes.
Surely theories with empirical content can be falsifiable if there's some prediction they make which isn't fulfilled.
No, that is not the case, and you will see why that is not the case later on. But since you ask the question, That has a particular reason. You know, a theory is a system of statements. And the question is now, what defines the identity of a theory? So are there certain modifications where, say, it's still the same theory? And you say, well, there's a certain periphery. And certain hypotheses in the periphery, if you change that, that doesn't change the theory, but there are certain principles in the core. Now, to have a deductive implication, you need these peripheral assumptions. So you have a prediction which turns out to be wrong. It's not clear whether you just change something in the periphery, then you would say, well, the theory is still alive. We have improved it now. And this is, so I already revealed now to you what's going on here. This is the reason. It's a different thing than statistical generalization. It's really a different thing. But on this reason, you say there's a so-called, there's no strict falsifiability. Yeah. Thank you for the question. Other questions? If not, then thank you for today, and until next time. Thank you.